Hello folks, here we go with 6-1 notes, and first thing I'd like you to notice is that to find a missing side, this thing that's called the law of cosines actually looks very much like, and here are actually 3 different versions, it looks very much like the Pythagorean theorem, with the exception that each one has this little extra piece on it. And this extra piece is the extra fudge factor we need to allow this idea to be used with non-right triangles. So again, like yesterday's law of sines, law of cosines actually works with all triangles that are not right. Again, if we do have right triangles, we can simply use trig and the Pythagorean theorem to find missing parts. In part 2 here, if we simply rearrange the formula, we can come up with a version that helps us find missing angles. It'll isolate the cos of A, cos of B, or cos of C term as we go. Okay, so let's get rid of some of this here and actually think about some problems. So as a change, what I decided to do today was to have us do some examples from your practice page that you have in your hands today. So we'll do number 1, 7, and 16 as examples. In number 1, we're finding just one side. In number 7, we're finding an angle. In number 16, we're solving the entire triangle. The 3 types of things I'll be asking you to do. So for trying the front page, I want to pick this version. And it's not too hard to remember what this is. Basically, it's the Pythagorean theorem and this extra little fudge factor. Notice the letter you're solving for starts the equation. The cosine of the same lettered angle ends the equation. Right? And have a look right here and find out which of the angle versions we need to use. Again, notice some of the symmetry in the problem. It's simply, in the equation, it's simply rearranging the other formulas. So just a quick peek at the first one. If we want to find the cos of A, notice the A squared is at the end. If we're looking for cos of B, the B squared is at the end of your numerator. And the same thing for the cos of C and the C squared. And the other parts are the B squared plus C squared. You always minus that matching letter on the bookends. Kind of like what happens in here. You have these bookend letters, and there's a subtraction here. The other 2 letters happen to get squared. So there is some symmetry. There's the A in it. Let's continue to a new page here, and I'll simply recreate the triangle that we have in example 1, roughly. B is here, 29 is here, 41 degrees is in that corner, C, A, and 13. So notice here, just by location alone, I have values in side, angle, side order. That's a key that you'd be using the law of cosines. Anytime you're using the law of cosines, you are always solving for the side across from the angle that you know. And if that is the case, this tells us which of the 3 versions of the formula to pick. So here we go. I have C squared equals A squared plus B squared minus 2AB cos of 41 degrees. And from here, it's basically straight calculation. Even though it's simply calculation, things can go wrong for you here if you're a little bit careless. So the first thing we want to find is, so what we want to do first here is square the 13, square the 29, and go minus 2 times, let me calculate it here, 13 times 29 times 2. That gives us 754 times cos 41, which we'll go find now. That's a decimal, of course. Cos 41. That's 0.7574. Rounded, we'll actually use the full value. Here's the biggest mistake kids will make. They'll add these 2 together, then they'll subtract the 754, and then they'll multiply by that cosine decimal. I think you probably realize, though, that is a major error. What you're really subtracting is the product of these 2, and you always have to multiply before you subtract. That's simply order of operations. So this will end up looking like this. These two add to 1,010, and we're subtracting the product of 754 times the cos of 41. We get 54069.05 and more. Use that whole number on your calculator and simply subtract from the 1010. Last step, that is actually c squared, so don't forget to, here at the end, you actually need to square root that last value you get. So your answer turns out to be on the order of the other side length numbers. And that's it. And the sheet tells us then to round to the nearest whole number. I got something like this. So rounding to the nearest tenth, I actually get 21.0 for this answer. And that is what the answer key tells me it should be. So that's if we're solving for a side. If we first, not that different for an angle, like in number 7, and let me recreate the triangle in number 7. We want to find the measure of angle A. So I have a triangle that looks something like that. So now let's label with our numbers. We have 9, 6, and 14. And the angle we want to find, it is best here to try to find the one across, the one that's obtuse, the largest angle. Reason being that the cosines of angles that are obtuse come out to be negative. So that's something we might anticipate. So the letter given there is letter A. So I will choose the formula from the previous page. Let's find my picture. So cos of A equals this larger fraction. There's a 2 on the bottom, and the A squared is here. My 6 goes here, my 9 goes here, 6 squared there, 9 squared there, and this would be my 14 number. Okay, so now do a little math. Be careful if you're typing this into a calculator. It's necessary to use parentheses if you're going to type it in one string. If you hit enter after you type the 14 squared, you will be perfectly fine. So let me find a calculator and work this through. 6 squared plus 9 squared minus 14 squared is negative 79 over 2 times 6 times 9, which is 108. And as we anticipated, we get the cosine of angle A being negative. If I take the inverse cos, essentially, of both sides, and pull this answer down in, second cos, second negative sign, it tells me 137.01 degrees. And I think more efficient here, it says record answers to the nearest tenth. That would give us 137.0 for angle A. And when working with law of cosines from this point, since I now have this answer number I can put up here, to recreate that without looking too far here. Get it? Oop, I